Hey, welcome back to Math with Patrick. Today is February 19th, and we got problem number 50 from this Daily Epsilon calendar. All right, let's do it together. How many times does a digit 4 appear among all two-digit numbers? All right, one way to do it is just count. There aren't that many numbers between 10 and 99, but let's count strategically. We're trying to find the digit 4, and you can see that we have some 4s here because in this 14, 24, 34, 44, all of these numbers are going to have a 4 in the ones place. And that's going to be 9 of them because I have 1 for my 10s, 20s, 30s, 40s, 50s, all the way up to 94. And so that's 9 distinct 4s. That was a 4. I meant 9 distinct 4s. Okay. The other 4s that we're going to find are in the tens place of all of our 40s. And so here we're going to have 40, 41, 42, 43, 44, 45, 46, 47, 48, 49. And then so in all of our 40s, counting in the tens place, we will have 10 4s. And one important thing to keep in mind is I don't want to double count things in these counting problems. But fortunately, I avoided that by only looking at the ones digit and only looking at the tens digit. Specifically, it's this 44 right here that might cause us some trouble. But since I was just counting the ones places, and there's 9 4s there, and just counting the tens places, there were 10 4s there, then I know that I can add up this 10 and this 9 and make a 19, which is today's date. There's another way to do this, and I want to show another solution before I finish the video. Sometimes when you do counting problems, it might be easier to count the things that don't work for your problem and then subtract from your total. In this case, it's a little bit silly. I think just directly counting all of our digits or our number 4 digits was just the easier way to do it. But I at least want to show a slightly different way to reframe these counting problems, just in case you might come across a harder one. So instead, I want to count all of the numbers that don't have a 4, specifically all of the 2-digit numbers that don't have a 4 in either of the digits. So you can think of me constructing a 2-digit number by thinking of how many options do I have for my tens place, and then how many options do I have for my ones place? Well, okay, for it to be a 2-digit number, it needs to be 1 through 9, but then I really, really don't want to have a 4. So for my first digit, it could be any number 1 through 9, but not 4, and that gives me 8 options. And then after I have my 8 options for my tens place, now I need to think through, well, how many options do I have for my ones place? This time, 0 is totally allowed. I could have 80, that's a 2-digit number, but I still can't have a 4. So then I have 9 different options for my ones place. And when you're kind of counting the number of ways you can do something, usually multiplication is the way to go. So if I have 8 options in my tens place, I can multiply it by that 9, the number of options for my ones place. And that gives me 72 numbers that don't have a 4. Specifically, 2-digit numbers that don't have a 4. And there are 92-digit numbers. They go 10 through 99. And you could count those if you want. There are 90 of them there. And so if I do all of my 2-digit numbers minus all of my 2-digit numbers that don't have a 4, I am left with 18 2-digit numbers that have at least one 4. Now that's not the 19 that we got earlier because this 44 is special. This number here has 2 4s in it instead of just the 1. All of the other ones just have 1 4. So for 17 out of these 18 numbers, I just have 1 4 in them. And then this 44 is special and it tacks on 2 4s. And I get the 19 that I got already. This kind of backwards counting might be really useful for the kind of question where you're asking, how many 4-digit numbers don't have a 3? Or how many 4-digit numbers, rather, have at least one 3? And those are the kind of problems where you might want this everything minus a subset. So I just wanted to show that way of solving it as well. Either way, there's just 19 of them. I counted them up already, so We're all done. That's the answer. I'll see you tomorrow.